Having said that, so this is just a further explanation. Sometimes we can load eccentrically, and then we have maybe deformed shape like this. So Q is the vertical load, M is the moment, and then figure 16.18b, this one shows a force system equivalent to that shown in six, this is the in terms of moments and shear forces, but now this is the force system equivalent, and this is showing the pressure distribution. So the distance, if you want to find the eccentricity, would be the moment divided by the Q. Of course, the moment is is usually either Q is the force times the distance. So that's the point. And so if you from these beautiful equations we already have that the sigma is the maximum could either be Q over BL plus M, right? 6M actually, 6M over B squared. No, not B is not squared, sorry. BD squared, all right? But BL squared, sorry. Mm, just a minute. BL squared, right? B squared L, sorry. B squared L. So if in this equation we substitute M equals QE, and then you end up there. The same for the minimum equation. If you substitute M equals QE, and then you end up here. So note that in these equations, when the eccentricity E becomes B over 6, so you can imagine if you substitute E equals B over 6 there, this becomes 0, Q man becomes 0, and Q max. So let's see, Q min is 0. That's true because this would be 1 minus 1. For E greater than B over 6, Q min will be negative, which means the tension will develop. Because soil cannot take any tension, there will then be a separation between the foundation and the soil underlying it. The nature of pressure distribution on the soil will be as shown in 6.18. So already what we've seen here. But so we are saying that for some distance, B over 6 is a key that separates when soil takes tension. So we always when we talk about eccentricity, we always control it by the value of B over 6, because that's important. So always a B over 6 is an important a figure for important reference for eccentricity, because so we already talked about this. And so the value of Q max is, then this is from Tomlinson. So the exact distribution of pressure is difficult to estimate. Figure 6.19. 6.19 is this. 6.19. So we are saying that 6.19 shows the nature of failure surface in soil for surface strip foundation subjected to eccentric load. The factor of safety for such type of loading against bearing capacity failure can be evaluated, of course, as the ultimate of the load. So the ultimate we already from the factors. If you want to see FCI, FC, if you want to FCD, FCS times NC. If you want to express this equation in terms of the Meyerhof factors, so CNC and Q, of course, FSC, Q, FC, okay, sorry, QI, FQD, QS times, of course, the NQ plus half gamma times the factors F, gamma I, F, gamma D, F, gamma S, gamma S times the. So either you express in terms of the Meyerhof factors, or if you want the traditional, the Terzaghi, 1.3 C and C plus Q and Q plus a half gamma B and gamma. So I forgot B here. Anyway, the same kind of equation, if you choose, if you want to use the Meyerhof factors, of course, the one for Meyerhof is a little bit more general because it's taking care of factors like compressibility, the shape, inclination, and so on and so forth. So either way, if you want to find your ultimate bearing capacity using Meyerhof, or you, of course, when there's no, the loads are vertical, the soil is not compressible, and so on and so forth, then the equation goes back to the one for Terzaghi. So where QU is the ultimate load, QU is two-way eccentricity as discussed below. For one-way, of course, we already talked about one-way eccentricity. So QU can be determined. Well, consider situation in which foundation is subjected to a vertical ultimate load Q alt and the moment M as shown in figure 2.5a and b. So this is figure 6.25. So there's QU and some moment. Excuse me, and we have two directional moments. So so as shown. So for this case, the components of the moment M about x and y axis can be determined as mx and my respectively. C 6.25c, and this condition is equivalent to load QU placed eccentrically on the foundation with x EB and y EL. Figure 6, not that, okay, not, of course, E, because we already said the moment is Q times E. So therefore, you can see the reason for that equation. So D, so either if you you can express this way, or if you want to talk about eccentricity, so that the Q is here and Q is here, eccentric about x and also eccentric about y, or you because here about y axis About y-axis, the load is here, and this is the y-axis, so it's trying to bend the y-axis like that. But about the x-axis is trying to, so this is, you can see mx, and let me use a different pen so that you see that is mx, and this direction is my, as uh, already shown here. So if QU is needed, it can be obtained from equation 6.56. I already also have maintained the equation. So 6.56, yeah, this is the equation 6.56. Actually, I forgot to name. So this is equation 6.56, which is the Meyerhof equation. uh, this is equation 6.56. So where Q is the Q times the effective area. The ultimate load is the ultimate bearing capacity times the effective area, and we already talked about this previously. And to determine the bearing capacity, you take care of the compressity, the shape, the shape, inclination, and compressibility factors. So as before, we will evaluate FCS, FCD, and FCI. Table 5 already as shown in the previous notes. So we use the effective length L and effective width B instead of L and B respectively to calculate FQS, FQD, and FQI. We do not replace B with B. So to calculate, sorry, to evaluate these ones, we use the effective lengths L and L prime and BI. So the factors related to cohesion, you use the effective breadth, effective length. But to calculate the overburden, the factors related to the overburden, the correction that is, we do not replace B. We use the original. We don't use the effective B or effective B, so to speak. In determining the effective area A, the width B, this should be B prime, the width B prime, and effective length L prime. There are five possible cases that may arise. One, so I'm just trying to explain. Remember we said the two-way eccentricity. So case one, where the EL is greater than 1 over 6. EL, this one is greater than 1 over 6. And remember the 1 over 6 has something to do with the eccentricity. The eccentricity not being more than B over 6. So has something to do with that. So if EL is greater or equal to 1 over 6 and EB over B is greater or equal to 1 over 6, the effective area for this condition is as shown. So if the eccentricity is between that, then that is the effective area, which so there's B1 and then L1, and of course this is a triangular area, so the area is half B1 L1. So that's the first. So therefore, B1, you can do your manipulations. This is just geometry now. So then, if that is the case, we can express B1 in terms of the eccentricity, and L1 also in terms of the eccentricity. So the effective length L is larger than the two dimensions B1 and BL1. So the effective width is A over L. So that's the first case. So because to get the bearing capacity, you need the values of B prime. You remember this, B prime and L prime. So with the eccentricity, you are able to now to you already know what B prime is, what L1 is, B1 and B prime and L prime are. you can substitute back in the equation to get the bearing capacity, because that's the key. Another case, we can have 1 over 6 is less or equal to EL over L. Remember, the 1 over 6 has something to do with either L, the eccentricity should be L over 6 or something, B, either length L over 6 and B over 6. Those are the reference values. So, and EB over B is less than 1 over 6. So 1 over 6 is less than EL over L, which is less than 0.5, and EB over B is less than 1.6. The effective area for this case is shown. So either so then the effective area is half L1 L2 times B. I think we should see the so this is the case. This is the case. Now, luckily, we have someone already did the research and drew for us either L1 over L prime or L2 over L, and the eccentricity over L. So you use this figure at in the solution, and this is from this Journal of Geotechnical Engineering, and by these people. So the effective area, because we remember our aim is this one, to get the bearing capacity, and the bearing capacity, you need L prime and B prime. All right, for the first for the first uh, for the first term, and also you need A prime. So so you can determine B prime this way, and you compare L1 and L2, which either of them which is larger. So L1, L2, whichever is larger, and then the effective width, the effective length is either L1 or L2, whichever is larger. So so we solve that actually. So L1 and L2, whichever is larger of the two. And then this is some area. Remember the first one, where in the first condition the effective length was there. So here we have kind of a trapezium, so the area is easy to find. So you have your area and B, and you can determine the L prime. So another case, we can have E over L, the eccentricity in the lengthwise over L is less than 1 over 6, and also 1 over 6 is less than the eccentricity divided by the breadth, which is still less than 1 over 6. The effective area is as shown in the so this is the case here. So the magnitudes of B1 and B2 can determine from figure 6.28. So again, we are lucky. We have been drawn a figure of B1 over B or B2 over B, and against the eccentricity. So your job is to know how much your eccentricity is, and how much is B1 or B2. And all these things are related to the once you know your the B and the L, and you can use these figures to uh, to uh, to to shape your, or to make dimensions appropriately, because actually in such cases, of course you will know your B and the L and the E, because you decide how much depending on the dimension. So once you know this is E over B, you have the figure, so you can decide how much B1 or L2 is based on these dimensions. Now case number 4, E over L is less than 1 over 6 and E over B is less than 1 over 6. So figure 6.29a shows the effective area for this case. The ratio B2 over B, thus B2 can be determined by using the E over L curves that slope upward. Similarly, the ratio of L2 over L, thus L2 can be determined by using EL over L curves that slope downward. The effective area is this is just the a trapezium which you can is it a trapezium? No. Okay, so, but you can divide into regular shapes and geometry. That's what I'm saying. Again, here you will know your E, you will know your B, and you will know your L. So based on these things, you can see here B2 over B. So when you have E over B, then you decide which value of B2 or L2 can be used. And lucky that there's some nice curves that have been drawn for us that excuse me, that may be used to help us in solving. And we can decide to have a circular foundation. So in the case of circular foundation under eccentric loading, this is the figure shown. The eccentricity is always one way because a circle is the same. The if you decide to draw the radius anywhere is the same. So the effective area and the effective width for the circular foundation are given in non-dimensional form in table 6.10. Once A prime and B prime are determined, the effective length can be obtained as this. So this is the table. So this is the eccentricity over the radius and then A prime over R squared and B over R. So these tables can be used because again you will have known the R and then you decide based on the R. You of course you will know E and R, right? So by the ratio of E and R, then you can read from this table what A prime over R or B over R squared or B prime over R is, and then you're able to decide the other dimensions as well. So there's an example here for you, which because based on eccentricity. So again, just to go slowly, if you have a question you're gonna ask. So excuse me. So for a square foundation is shown in the figure with eccentricity EL 0.3 in the x direction, and in the y direction the eccentricity is 0.15. So we assume two-way eccentricity, and so the issue is we need to determine the ultimate bearing capacity or the ultimate load. Sorry, the ultimate load. The ultimate load, remember, is equals to QU times the effective area. So here because we already are given the eccentricity in the x direction is 0.3 and then the length is 1.5, so 0.2. The eccentricity in the y direction is 0.15. So from the so these figures here from the figures here, yeah, from this figure. Okay, let's see. The excuse me, we are saying that EL over L, one of them is 0.2. Let's see. Just to show you how to read one figure. E over L is 0.2 and EB over B is 0.1. So let's see. Sorry. So EL, yeah, EL over L is 0.2 and EB over B is 0.1. So here, where it meets this value, you can read down you can read, let's see, maybe some value there. Let's see how much they get. About 0.85, really? Okay, unless let me be sure. This is 0.2 and 0.1, so let's go back. No, okay, this one, sorry. The which curve is it? Let's see. Unless we're not reading the right thing. 0.85. 0.01 is this one. Okay. 0.01 is somewhere. EB over B, let's see. I think these values are wrong because this is wait. Yeah, because then if you divide 0.15 millimeter, that's it, divide by okay, 0. Yeah, see that's 0.1 and 0.3 divided by 3, 6.27 A. Okay, let's see. From shown in the case similar to that shown in 6.27 from figure 6.27b to 7b, right? So 0.1, unless I'm reading my own stuff. 0.2 is here, right? 0.2. Something is wrong with the reading. It's about 0.2. L1 over L is 0.85. Just a minute. Yeah, and then L2, again the same thing. Just a minute. There's some. So for please note the following. There are two of them. One of them is here. So actually there's no error. You can see that there is one value here, 0.1. You can see. So if you extend, actually there are two of them because what we are reading is for B2 over 2. This is what we are reading here. And not actually, that's not the that's not the. So we are reading for L2. He says 0.21, which is correct here actually. You can see, but you can see there's another value here. You can see there's another 0.1 here. So if you project, then it's about the 0.85 exactly. Yeah, so please note that. So then actually it's correct. There's no error at all. Yeah, so L1, so that's how to read L1, 0.85. So those are your ratios. And the L2 is 0.1, agrees exactly with what we have found. And these are the dimensions. And then you follow the formulas to get the area, L1, B1, and then you apply the formula, and the C is 0. So from this you get your Q as 12.6, and then from the tables we already have, in this book the tables are 6.5, but in our case they are table 1, 2, 3, and table 5. In any case, when C is 0, the values you can see. I don't know, maybe I show you when phi is 30, so just to see how you get these values. But that would involve, anyway, you can see table 1, 2, 3. When phi is 30, you get NQ and gamma as those values. Or you try to substitute there. There are some formulas I gave you. I should give you around the same value. And so therefore this is from table 5. These values are from table 5. These are the correction factors from table 5, and then this value is 1. Then if you substitute the area times Q, you remember now area would be B times L, and then the QU is determined as shown, and then you get a value of about 606. I know some of you think this is very hard, but you can see it's just arithmetic. It's just if you follow the formula and follow the curves, there's nothing very difficult. And okay, I'll stop. If someone is confused of where to get any of this, you should ask me. You should check this from table 5. These values, how to get the correction factors, these are from table 5. Table 5. If you have notes, you can check. And if you can't see, you can ask me right away from table 5. Now, these values here are from tables 1, 2, and 3 of the general bearing capacity failure. So we said only N gamma that changes a lot for different researchers. For NC and NQ, they're the same. So make sure, if you can access the table, see where phi is 30. If you can see these figures, 18.4 and 22.4. And if you don't have, you can ask, because that is, if you can't see, you can ask. That is the only reason why you'd think this is hard. Otherwise, once you get these values correctly, and I think I've demonstrated sufficiently how to read them. .85 you can see, and then 0.21. So this is for B L1 over. So you can see here. So from this side, this way, you obtain L2 over L. So this is the separating point. So this way you read L1 over L, and this way you read L2 over L. Yeah. So always, if you note, so L1 over L, 0.85, and going this way. Yeah. So once you get that distinction, then the rest is just mathematics. So I stop there, and yeah. So and then okay, we proceed. I believe now you can find your way around. And then of course there is a simpler way proposed by a simpler way to do this. So there's a simpler approach to compute the ultimate bearing capacity. Of course, you should note that when it's simpler, then there is a likely that you're under or overestimating. The error is a little bit on the higher side. So under two-way eccentric load is discussed here. The foundation of dimensions B and L with the column load acting with the eccentricity EB and EL is shown in 6.32. We can see this. This is a very simplified method. So if this is eccentricity, then we are saying the effective length. This is related to the effective length actually is B minus 2E. Now, this guy assumed that the effective length now would be B minus 2E. Sorry, that's for B. And the effective length, again, effective length would be L minus 2E as so Meyerhoff's suggestion by neglecting the light yellow area. So we neglect this part, the light yellow. This is what we are saying. We ignore this part and assume that the eccentricity reduce the so we only have that effective area. The light blue part is the effective area. So this is a very simplified way. So as shown in the figure, the effective area of the foundation is that B prime times L prime as already discussed in the bearing capacity equation and the computing. So here we are not going to belabor the point a little bit too much, because you remember we only need B and L prime and the A, which has been very simplified. So if you have B, then you know that B prime would simply be B minus 2E, and L prime would be L minus 2E. That's all. So already you have your B prime, L prime, and A prime, and you're good to go. So again, I think this is too simple, honestly, for me to go through. You should be able to do it yourself. So using the simplified method, this should be a piece of cake for you. So I will not go through that. Sometimes we have so bearing capacity of continuous foundation subjected eccentrically inclined loading. So we shallow continuous foundations are at times subjected to inclined loads. Figure 6.33 shows two possible modes of load application. In this figure, B is the width of foundation, is the load eccentricity, Q is the ultimate load per unit length of the foundation. In figure 6.33a, the line of the load application of the foundation is inclined toward the center of the center line of the foundation and was referred to as partially compensated by Perloff and Baron. Those two people. It is possible for this line of load application. So just to widen your scope a little bit, it's not necessary that all the time we'll have only vertical load. So if on a steep foundation, we have a load that is inclined at some eccentricity, so it's possible also they can be inclined away from the from your from the center line. I leave this to you to think of under what conditions you might have this thing happen. Under what condition uh, do you think we can have this kind of loading? So, so Perloff and Baron in 1976 called this type of loading a reinforced case. And there is the results of practically all studies relating to bearing capacity of shallow foundation subjected to an eccentrically inclined load presently available in literature. Though fairly limited, consider the partially compensated case. The following are the procedures used to estimate the ultimate load for both cases. So Meyerhoff's effective area method can be used to determine the. So all this we already know. These are the factors, correction factors based on shape or compressibility or inclined load. Okay. So note that for continuous foundation, all these things are one, and then B prime. So we use the Meyerhoff, the simplified way. So using these values of the bearing capacity given table 1, 2, 3 we talked about, and the depth factors given table 5, the value QU can be estimated. So from there, the value QU can be estimated. Know that QU is vertically, is the vertical. So this is the vertical component without the inclination. So so this is the is the vertical component. So the if you want to get the sorry, the load in the direction of the inclination, then this is how you correct, because remember the load is inclined as at an angle beta from the vertical. And so so this how to estimate the component in the vertical direction. And based on larger number of model tests, Patra proposed some reduction factor for the foundation. So this would be the ultimate times the breadth times some reduction factor. Now the reduction factor, okay, this is the ultimate bearing capacity. We already know that, of the foundation with a eccentric vertical loading. So if E is 0, beta is 0, the reduction factor can be expressed as follows. So if you combine this equation 6.87, so this and that, then this is how to determine uh, the the load. But this just for information, just so you know, because if you find this on the in the field and you have the note, so this is how to determine that particular load. And so for soil, actually for granular soil, the reinforced case, this is okay, but this is empirical. This is empirical. You should note that they're of the same manner, except the difference is in this. Let's see, 1.5. You can see, you can note this. Those values are a little different. So this is just to make sure you know and have an idea of all manner of scenarios that you may find, and who and to you if you find them and then you say we were not taught. So that was brushing off on the just doing some finishing bits. Uh, so there is what you call mat foundation actually. Just some introduction and we can end. Uh, mat foundation sometimes you have because okay, for typical cases and when the soil is good, so that when for example in your layout, the structural drawing in your layout, so this is your probably your building structure. So in most cases you just put your columns there, the columns there, columns there, columns there, and you design individual bases for those columns. So they're either called pad foundation, mostly just called pad foundation. So if you draw the cross section of this, you see the column like that, and then with the foundation, uh, and probably you draw a cross section, maybe 300, I don't know, 300 millimeters by 300 millimeters. That's your foundation. So normally for this, for most of these, the individual foundation or pad foundation is just okay if the soil is good enough and it's economical for most cases. But sometimes when the soil is very weak and the loads are a little bit much, you need to have one mat, like all this, so or the whole of this thing. In fact, there's no way to undo this. But for mat foundation, it means you have series of columns, but all you see the layout of that thing is all of it is going to act as one foundation, like that, like this, like that. So many columns there, but the entire thing will act as a the entire thing like that is gonna act as a foundation. So what you will do is consider the individual loads on these columns and then find uh, the center of each of the individual columns, and find their center and how far from the edge they are. So you find the effective the centroid, or so to speak, and then from there you can do uh, the the foundation. Most of the time this is done because the soil is not very good for soft soil, and so the mat foundation serves to spread the massive loads over a larger area, and probably so that they're able to be carried effectively. But as you can imagine now, this will take a lot of space. So only if you have the space, because otherwise, if you don't have the space, then you're gonna be also in trouble. So just a little bit of introduction. We'll delve this in this into this a little bit in detail in the next class. So the types of shallow foundation discussed previously are called footings, already said. Under normal conditions, these square and rectangular footing are economical for supporting columns and walls. However, under certain circumstances, it may be desirable to construct a footing that supports a line of two or more columns. These footings are referred to as combined footings. So, sometimes, like I said here, uh, sometimes to sorry sometimes to do, for example, this is your column, uh, and this is your column, sorry, and this is your column. So normally you do individual bases, but sometimes someone is talking, please mute your mic. So most cases the individual bases are just okay, but sometimes you don't have the laxity, so you have to combine the footing. So for two columns you have one footing. That's what we're saying. So when more than one, I already said combined footings, but when more than one line of columns is supported by a concrete slab, it is called mat foundation. I already said. So you could have a series of combined footings. So here, sorry, maybe, sorry, this line here, line there, and they have a combined footing, and there, and there, and there. So if these have a combined footing, these have a combined footing, then probably it's better to do a mat foundation. That's what we said. But we can classify them generally as follows. the is trying to misbehave. Okay. So we have rectangular combined footing, trapezoidal combined footing. We have strap footing. So mat foundations are generally used with soil that has low bearing capacity. I already said this. Mat foundations are used under the following circumstances: when more than 50% of the structure's footprint will otherwise be constructed as part a foundation or steep foundation. So I have said already, if most of the more than 50% is gonna be just the pad foundation, and probably the pad foundations, if you try to shape them, they overlap each other. So it's better to replace with one pad, one big pad. In other words, mud foundation, just like the mat, is one big pad foundation, but now it's supporting several columns. So when the type of structure requires that the differential settlements be limited, very small values. Also, yeah, because once you have one large pad which is rigid, of course, it spreads the pressure. You remember we said sigma is P over A. So the pad is increasing the area. What we are doing with the pad is such that the area is very high. So when the area is very high, or increase the area to very high, then we are reducing the stress, and hopefully the settlements differential eventually will be limited. So where there are non-uniform soil conditions, or where the soil pockets of weak, so you may have good soil actually. You may have good soil generally, but sometimes a little, maybe some regions here, some regions there, some regions there is weak soil. So the pad, what the pad does is it takes the load from the weak areas to spread over, because it's, the pad is rigid. So so if this place is weak, then it might distribute the load or extend the load over areas that are relatively strong. So, a kind of helping or preserving the weaker, the pockets of weak soil. So that's the beauty of the pad. But you see that it requires a lot of space. So sometimes if you don't have that space, you have to think otherwise. But for the present case, then we need to talk about the pad foundation. That's what we're gonna do. So in several instances, the load to be carried by a column and the soil bearing capacity are such that the spread footing design will require extension of the column foundation beyond the property line. I'll show you this in a moment. I think we already talked about this as well. Very common also in Nairobi, because you put your column at the property line, and you cannot extend, for example, the foundation to someone else's property. So you have to. So this can be avoided by having two or more columns supported on a single rectangular foundation, as shown in Figure 10.1. If the net soil allowable pressure is known, of course it has to be known, because this is why site investigation is important. The size of the foundation would be B times L, just to see what we're talking about. Excuse me. So you have two, column 1 and column 2, and so this is the same thing we are doing. uh, 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 as Because you need to find the centroid, the distance to the centroid of this. So you can take this distance 1, let's say L1, and then the distance to the edge, to the centroid of that, L2. So to define that distance x, so, and then you should also this distance x bar. You should know this, but now q1 times L1 plus q2 times L2 should be the same as q1 plus q2 times x bar. You know this, you know that, you know that, you know that, you know this, so you can calculate x bar. That's what we are saying. But the point is that all this, so because designing individual parts is not possible, and this is a property line, so by combining the footing, then you prevent the footing from extending to someone else's property. So like already we've said, the area would be q1 over, of course, the q allowable, the net. All right. Of course, this is this q allowable net is normally q minus q over the factor of safety. We already know that 3 could be 3 or 5. Between 3, factor of safety should be generally between 3 to 6. We already know this. So q1, q2 are column loads, the net allowable by soil bearing capacity. Some error there. So determine the location of the resultant column loads. Already this already done this, already did this. So already say this is q1 l1 plus q2. Anyway, you guys, I believe you are sufficiently good in maths, or whichever way you might think is good to determine. But typically, this is the most efficient, quite easy, x bar. So this is how to determine the centroid. So of course, this is a derivation from this principle, and so for a uniform distribution of soil pressure under the foundation, the resultant excuse me, the resultant of the column load should pass through the centroid of the foundation. Thus, so L. Okay, this is just some calculations based on geometry. Based on geometry. So where L is the length of the foundation, once the L is determined, the value of L1 can be obtained as follows. So the L1 is L minus L2 minus L3. Note that the magnitude of L2 will be known and depends on the location of the property line. So just to be clear, L2 is the distance from the property line, basically. So L3, you will already know. Of course, you know L3, the distance between the columns, you know L3. L2 is the distance from the property line, of course, and then you can determine L1. I mean, should be, that's just geometry anyway. And then the width of the foundation will be the area over L. And then this is computed from that equation. So and has to be less than is less than L2 plus L3. It should be increased. So if you calculate L, because L should be the entire thing, so if it's less than you can see here, if L is less than L2 plus L3, then there's a problem, because L2, you can see L2 plus L3 should be less than L. So if L, no, okay, L2 plus L3 should be less than L. But sometimes if you find that these are more, then you need to increase. Uh, uh, you need to increase so that because you should need to increase such that L is greater than L1. Sorry, L2 plus L3. That's what we are saying. Then the two columns here, the resultant is not acting on the centroid of the base anymore, and the pressure distribution becomes non-uniform. Okay. So that is for the for a triangular footing, uh, triangular combined footing. Then I think we have an example at the end. I'm not sure whether it's triangular or trapezoidal. We see for trapezoidal combined footing. See this figure. You can have combined footing trapezoidal. Uh, is sometimes used as an isolated spread footing foundation of columns carrying large loads where space is tight. The size of the foundation that will uniformly distribute pressure on the soil can be obtained in the following manner. Again, A is Q1 plus Q2 over Q allowable as previously done. The same thing we've done previously, but now the length is, the shape is trapezoidal. Again, the same thing. So from the figure 10.2, from this figure, that's geometry. You need to at least attempt to prove, not even prove. This the area of this. Should be fairly straightforward. And then again, how to get x bar from the same idea. And then from the property of a trapezoid, where the resultant column load passes through the centroid, this has to be true. So with the known values of A, L, X, and L2, equation 10.7, 10.9 can be solved to obtain B1 and B2. Note that for trapezoid, this has to be true. Now there is one, unless there's a question, there is what we call cantilever footing. This is actually this is more of structures than foundation, but of course. So for cantilever, excuse me, we not say a lot about it. It's just a combined footing, but now this is designed as a beam. That's all. So it's like more of concrete design. So this all this because it's is the is a combined footing, yes, but because you join the two loads, then you design that more or less as a beam element. So cantilever footing construction uses strap beam to connect. I think already said strap beam. So basically the one the mode of carrying, because beams carry load by shear. This is uh, the the mode of carrying of loads for beam elements. Beam, for example, even floors or also, but columns carry load through compression. So yes, so uh, strap beam connect to an eccentrically loaded column foundation to the foundation of an interior column. See the figure. Cantilever footings may be used in place of trapezoidal or rectangle combined footings when the allowable soil bearing capacity is high and the distance between the columns are large. If the net allowable soil bearing capacity is known, determine the area of the foundation. So basically, these are designed as beams. That's what we are saying. So you put the small footing on top, but this is designed as a structural element. That is designed as a structural element to help in carrying the load, to join the columns together and then carry the load. Because in this is it assumed you already taught how to design beams. So if this is designed as a beam element, you can do that. I think that should be no issue for you. So we have an example here for the trapezoidal, and I want to challenge you now because I want you guys to participate. I want you guys to participate. So I have left gaps here for you to fill. until we get the solution. And I want us to work together. So